you the link.
Welcome to Neuroccino, everyone, our weekly journal club. Lila just shared the link for today's paper. Thank you. I'm going to put that over on Zoom as well. The rules of the game, everyone is welcome to join us and present a paper they're interested in, and then we discuss it to the best of our knowledge. And today Lilith volunteered with a fantastic paper on reconstructing Pink Floyd. Lilith, take it away.
Yes, thank you. Well, let me share the screen. Can you see it? All right. So, yeah, this paper was published actually in the middle of August this year in PLOS Biology. And the first thing that captured my attention are two words, Pink Floyd in abstract. And I'm say, okay, neuroscience and Pink Floyd in the same paper, that's something that I would like to read. So yeah, basically what these researchers did, they tried to reconstruct Pink Floyd, a piece of Another Brick in the Wall, one of the famous pieces of that band, from auditory cortex of people with intracranial EEG. So they directly put a bunch of thousands, basically thousands, there are 2,000 electrodes in both hemispheres that were placed in the brain during surgery. These patients, there were 29 patients, and the placement of electrodes you can see here on the plot. Yeah, basically you see that there are lots of electrodes in both hemispheres, and these 29 patients, we have to keep in mind that they had epilepsy, and they had to undergo a surgery, and they gave a consent to do this experiment. So they put these electrodes, they turned on Pink Floyd, and patients were just listening to that piece, specifically around 190 seconds of the song. And I don't know if you could hear if I turn on here, but if not, that's fine.
No, I can't hear anything, Leonard.
Wait 1 second. Let me try again. Can you hear now?
A little.
Yeah, so basically, okay, so it's just 200 seconds of the song. And in the plot A, you can see the song waveform. And in the bottom, auditory spectrogram, where on y-axis we have frequency, and on x-axis is the time. Plot B, there are electrodes that you can see, and if you see the red one, it's on the plot C is the neural activity at the specific location. All right. So they collected this neural activity from all of these electrodes, and they tried to predict the spectrogram they tried to predict the neural activity based on auditory spectrogram of the song, which we can see here, using spectral temporal receptive field. It's basically a mathematical function that is used to define how our neurons would react in auditory cortex if we get a stimulus. So some sort of hemodynamic response function in terms of neural activity and Bell's signal, but now we're talking about how neurons would act if they receive a signal. And they used different models, non-linear and linear. Right now you can see the linear function where y is our neural activity that we want to predict with X, which is a spectrogram of the song. And here A and W are the parameters that will be trained during the algorithm training. And W is basically this receptive field, spectro-temporal receptive field that will be tuned in order to find the best, the highest correlation with the actual spectrogram that was presented to patients. Is it clear more or less? I hope so. Okay, so, and what they found is this. First of all, there are much more significant electrodes were in the right hemisphere than in the left hemisphere, but there were still significant electrodes also in the left hemisphere. The highest correlation was in the superior temporal gyrus of the right hemisphere. Also the highest in the inferior frontal gyrus, and so this one I think they called did they include it? Wait, hang 1 second. Sensor motor cortices, yeah. So they said that sensor motor cortices, superior temporal gyrus, and inferior frontal gyrus, and in others they included supramarginal gyrus as well, and everything else that is not included in these three big clusters of regions. So in these three regions, we see that there is a higher, the correlation was higher in the right hemisphere of these three regions. Yeah, so then they tried to different models, as I said, linear and non-linear. And you can see how they reconstructed the song. So the first plot in figure C, we see the original spectrogram of the song. Then the second line and the third one are the reconstructions, like directly from the neurons of patients. And as you can see, they are pretty similar with the first line, but non-linear model, which was two-layer, fully connected layer network, was able to reconstruct it more precise. You see the linear one is a bit more blurry, smoothed, which lack of details. And also if we want to be more specific with numbers, R squared for non-linear was 0.43, while for linear it was 0.33. So yeah, the idea is that non-linear was better to reconstruct it, meaning that probably when we are listening to something, our variables are not linearly connected. So there is some non-linear relationship is happening between the stimulus and the way we perceive a song. Yeah, and in the plot D, we can see just basically a reconstruction of one patient 29, from specific one brain. Yeah, so on this plot also, they also try to see which other factors can impact the accuracy of the reconstruction. And one of that was, as I said, the type of the model. The second one was how many electrodes is needed to become pretty accurate at reconstruction. And you see that around 43, the curve starts to flattening. So they said that we don't need like 300 because there is not so much gain, and around 43, 50 electrodes, it's enough to reconstruct with the same accuracy the song. Also, they looked at the dataset duration, how long we need this song to reconstruct it. And it was again around 70 seconds, so no need for 180 or 200 seconds to predict with this accuracy. Another cool thing that I'd like to show you is this. So they got this reconstruction. They said that the right hemisphere has higher correlation, but also left hemisphere electrodes were also significant. And then they explained which factors are better, are helping us for the accuracy of the reconstruction. Then they tried to understand if there are specific electrodes reacting for, I don't know, pitch, vocals, instruments, and so on and so forth. The method that they used is pretty popular now also in fMRI analysis, is independent component analysis. So basically it is when we have a big cake and we want to understand which are the ingredients of the cake, like, I don't know, sugar, some berries, dough. And this is what we get from independent component analysis. We extract the components that compose our cake. So in this case, our cake is basically the bunch of noisy neural activities and so on. And we need to know which one is our berry, which is our dough. And they applied independent component analysis, and they found three components, which they called onset, sustained, and late onset. And in the brackets, you can see how much variance they explain. Yeah, so in contrast to principal component analysis compresses, and this one expands basically. And the cool thing is that the sustained component, right? Yeah, so you see here the neural activity and the reconstructed one, and the ones that are, I know, not reconstructed, I think. Yeah, I think it's the actual one. And the one that is above 0, they are colored in red. And these are the ones that correlate with a specific component. So there is a component sustained, and only here we have high correlations. And it's interesting that exactly this part corresponds to just 2 vocals. So lead guitar, synth, and other components of that piece is reacted by other components like onset and late onset. But exactly sustained one is just reacting for the part where you see the vocals. Yeah, I think that's pretty cool that this analysis allowed us to basically extract something that actually sounds a bit meaningful to us. I mean, you can see that it's not just pure coincidence. Yeah, another interesting part of this paper, and after that I'm finishing it, is this. They used ablation analysis. So what is that? Is that basically you build a model with this, 300 electrodes, and then you get an accuracy of how good is your correlation, basically. And then they took out artificially some electrodes, for example, all the electrodes from the left hemisphere. Then they have this model, and then they compute the basically the accuracy, and they see how is it significantly was this component important in explaining our variance. So if you are taking that out and there is significant difference, it means that that component was important. If you are taking that component and the model, and in comparison, there is no significance, right? It means that that component was not so much important. It was not significantly helping to explain the variance. So that's what they did. They did anatomical one and functional one. So first, let's look at anatomical one. As you can see, if you take out the whole left hemisphere, this one says that is important in explaining the variance. The same one as the right one. The same one if we take out superior temporal gyrus, all from both hemispheres, is also important, that region. But when we go here for the take out left superior temporal gyrus, it's not significant. So basically what this analysis says, that component was redundant. It's not actually explaining significantly our model. But if we take out the right superior temporal gyrus, then our accuracy drops significantly. Okay, and with other regions, nothing was happening. So the model was basically explaining the same amount of variance. And in the functional one, its functional is when we received these three components from independent component analysis. And here I just focus on one thing. So the one that was responding to vocals, basically to words, I would expect that it will be important the left sustained be significant. But when we're taking out the left significant, the left sustained one, it's not significantly, there is no significant results. So yeah, that was pretty, I don't know, interesting. Like you can think about the interpretation of these results, but maybe this can somehow tells us about, they don't discuss it, but I think can explain something about patients who have aphasia. Well, they cannot speak, for example, but they still can sing. And maybe there is this network that allows them to kind of perceive or respond. But here again, we're talking about only perception of the song, not production. Authors also separate that as a speech production and speech comprehension. So yeah. And also I like the way they finished it. They say, okay, we did that and that and that, adding another brick in the wall of our understanding of music processing in the human brain. I think, I don't know, it's pretty cool paper. really used the different interesting analysis, pretty heavy, like they tried nonlinear models with a lot of cross-validation, bootstrapping, so something to, it was interesting to read and actually share too. I hope it was clear. Any questions? Happy to talk and discuss.
Amazing. Yeah. Thank you, Lilith. Oh, hands are up. I think Anna was first.
Hi, yeah, thanks for presenting. I have two questions. So first one, maybe I missed it, maybe you said it in the beginning, but so how they decided on the coverage of the electrodes? Because isn't every result then highly driven by where they actually place the electrodes? Did they like have a rationale about where to place them?
Yeah, good question. It was the placement you can see here, and the question why they didn't, they skipped, for example, the whole occipital and parietal regions. Yeah. Well, they put electrodes in a way that it will not be correlated with the regions where they have epileptic, they suspect epileptic events. So the because these patients were with epilepsy, and they went to surgery, and the placement of electrodes, I think, was because they don't want to have artifacts with their condition. So that's why they kind of placed it in places where it will not be dependent on the epileptic activity, abnormal neuronal activity, basically.
Can I interfere shortly?
Huh?
Can I interfere shortly? Because usually it should be the other way around. The only way they're placing them there is because they're trying to find the hub of the epileptic seizure. So this is why it's so much in the temporal lobe, because this is usually where they arise. So it's kind of driven by the clinical, assumption of where it comes from. I'm sure they left out some while recording it or while constructing something, but the way they place them in the first place is usually clinically driven.
I just go and check. By the way, you can later go there and try to listen the reconstructed one. They're pretty actually similar. But meanwhile, 1 second.
Yeah, just to double up, I was going to say the same thing. So the placement of those electrodes is usually clinically indicated and not research-based. So you just hope that they're in locations that are meaningful for the research, but you can't really ethically go in and place them based on a research question when there's no clinical indication.
Yeah, I guess then, it was actually misunderstood their idea when they say artifact-free. So artifact-free in a sense that maybe there was not epileptic event at that point, but electrodes were placed in the places where to localize their epileptic foci. So sorry for misleading you.
Couldn't you
that's what we have Neuroccino for.
Yeah.
Couldn't you double check that with like as a researcher with testing like different songs, the reconstruction of different songs? For example, I was puzzled also by figure 6, where they were really reconstructing I think vocals, you said, right? Vocals from the neural activity. Did they actually prove it with another song as well? Because it might be just something that is very like applicable to this exact song.
Yeah, that's also a good point. No, I think they just decided to actually choose one piece from one song of one band to play it. So basically all their analysis was based on 200 seconds of the song.
Okay.
Yeah. But I agree, it can be really important to make a proof of concept, basically to try another part, and if see that the second component will actually move.
Or also just another song, not even the part, because there may, perhaps, I'm not sure, but there may come in like a factor as like inter-individual variability, like how, like whether some people, for example, know the song or some people don't. Maybe
Yeah,
that's something
that's
also that could be driven by that.
yeah, that's something when I was reading I thought about, and then in the end of the paper they put it as limitation that they didn't ask patients if they knew the song before or not, because they wrote that patients were passively listening. But what is this passively? We don't know. I mean, if a patient knows this song, I don't know if you can just calmly sit even you are under the surgery. I don't know actually, but you will still kind of maybe have your vocal cords moving with the perceiving the song. So it depends. It's important point, and that's what they put in the limitation in their paper.
That's an easy way to well, fix the limitation, to just ask before.
Yeah,
but
at the same time, if you look into this paper, it's super complicated and really rare papers like that, and at least some hints that allows us to future test in a more easier, more or less experimental designs, specific ideas that you can take from the paper, but no paper is ideal. Yeah.
Well, I guess asking for familiarity would have been feasible, and that's probably an oversight. But then in terms of testing other songs, I guess we have that classical clinical limitation of time during surgery. So there's only so much you can do given the time constraints. So 29 is already, I think, a very good size in that case to have that kind of data. And I don't know what the incidence of ECOG electrodes where you can do these studies with in a research center actually are, but I can imagine that having one song was a trade-off between feasibility and time.
No, yeah, also it was easy thing to ask, but yeah, it's always the easy things not always, but it's easier to forget about easy things, and when your focus is more on a more complicated analysis. But yeah, it's something that easy to ask, and also I feel like that many people would know this song, so I feel it will be more or less homogeneous among population, this song.
I think you will see a generational divide a little bit. Some people are laughing in the room.
A suggestion to try it with Happy Birthday. I think there we wouldn't have the generational discrepancy.
Well, they wanted to have fun a bit more.
And I mean, it caught your eye, right?
I know. No, I totally agree with this. Yeah.
Annie, you've been very patiently waiting.
Yeah, thanks for presenting it. It was all over the news, and I didn't bother to look into it myself, but just blinded by the headlines. And one of the questions I still have, maybe I didn't get it right, was aren't they trying to predict the neural activity from the song? So isn't it vice versa? So the title looks like they're looking at the output, and then from that they can read the song. But if I understood you correctly, they're kind of trying to predict what the output would like, or is it just that it complements each other? It's not like we could take the recording now from their brain and thereby say which song it is, right?
You mean we blindly basically taking some neural activity and trying to say if it was Pink Floyd or not? You mean that?
I mean, that's what it in pop
science. So in their design, they are basically doing that because it's not that they are taking like the whole song and they put the whole song, they go there and then go back. No, they use this idea in machine learning, like when you split your data into training, validation, and test. So basically the test one is something that we are trying to guess if it's how closely related to actual
okay, then I got it.
Stimulus.
Yeah,
and they did it like with a lot of iterations, so to have the robust result.
I see. Okay, that clears it up. And another one, the graphs you showed at the end, where you're trying to figure out which one you could drop. And I was just wondering if this is not just a rather fancy way to do backward deletion in the model. I mean, I like it. It's very visually pleasing to see. Oh, wow, it seems to have such a big effect to drop the both of the SDGs. Yeah, just was wondering what other people think about it. I like it, but it's not.
But which method did you name? Because maybe
I mean, in any linear or nonlinear regression, you could drop different factors and then.
Yeah, that's just I think that's what they did.
Okay.
Yeah, so
it looks really nice.
Dropping one factor, you do the analysis, and then you compare with ANOVA, I guess, and then you see if it's significant. Then that component was significant. If not, then it's basically you're comparing two same models. So yeah, that's what their idea.
Which is a classical backward elimination analysis, right?
Yeah, or hierarchical, yeah.
Sounds very cool at a collaboration.
Yeah. Virtual lesion. We perform virtual.
Which does make sense, yeah. Question on the same figure from my side. So they say if you take the left out completely, it has a significant impact. If you take out the right completely, it has a significant impact. But then, and if you take both STGs out, then you have a significant impact. But if you take the left superior temporal gyrus and there is no impact, do they then speculate in the paper why the left hemisphere is important if it is not the STG?
I'm really scared to say no. I think I should read it one more time, more detailed, the discussion, but I don't really remember that they discussed it. But again, this is Neuroccino, and I just went really superficial, but yeah, it's something. But I think I didn't find why no left sustained the one that was for vocals was not significant in explaining it. I think about that there was no discussion, but again, it's just I honestly I don't know. I don't want to take responsibility saying no in this case.
Fair enough. I guess I have to read it now.
That's why I presented, so
it's super exciting.
It is teaser.
And I love Pink Floyd, so I'm quite excited to actually read the paper. Right, we're slightly over time. Thank you so much for presenting the paper, Lilith. I think the slot for next week may still be open, so if anyone came across an exciting paper, just let me know and you can come and present it for next week. Other than that, oh, hang on. It's this week, right? We have a CNS talk this week. Yes, on Wednesday. So that is in 2 days at 4 o'clock. We have Gesa Hartwigsen talk about plasticity induced with stimulation. So do join us for that one. Wednesday, 27th at 4 p.m. On the usual channel. Other than that, have an exciting week in science, and I see you Wednesday. Bye.
Bye.